Okay, so we're pretty much done, like I said, but I do want to go through tutorial 5. There's a lot of stuff there that I think we need practice on. Just seeing the way people are going through the phasor homework, I think there's more practice needed with doing things with complex values and complex valued impedances. But that's okay, we've got time to do that. The two main things I want to do today are mostly to do with the things we haven't done yet. Use of a function generator and use of an oscilloscope. But I'll do that after we've talked about the tutorial. I have some of the stuff I forgot to bring last time, or I forgot to find last time. So we want to finish off the Thevenin and Norton lab. Those are potentiometers, volume controls, that you can use to do the maximum power transfer part of the lab, right? Now, there's a couple of problems with that. I don't have many of these. I've only got 10 of them. Even if I had more than, if I had one for every group, doing the maximum power transfer lab is a pain with only one multimeter. It's much easier to do have two multimeters, one measuring the voltage across the potentiometer and one measuring the current through the potentiometer at the same time. That way you don't have to keep unplugging the potentiometer and replugging it in order to do all the measurements. So the other problem I noticed last night is the lab says that these are 10K potentiometers. They're not all 10K potentiometers. Some of them are 1K potentiometers. If you get a 1K potentiometer, I don't want you to use 1K as the value of the resistance. I want you to use something less than 1K, say 150 ohm or 270 ohm, something like that. But it's pretty clear if you just look on the, let's see if I can show it on the screen maybe. If you just look at the top there, this one says B1K, right? So that's a 1K potentiometer, and let's see if I can show you a B10K, right? That one's saying B10K up at the top there. So it's pretty easy to figure it out. Okay. I'm just trying to think the best thing to do next. I think we started looking at tutorial 5, but we didn't actually do it, right? So I suggest that I'm going to do a couple of these, and then I'll get you to do them. Now, the nice thing about this is this is in the format of the final, right? So there's lots of questions, and they're in very similar format to the questions on the final. What I'm going to suggest is after I do a couple of example problems, I'm going to get individuals a particular problem and get you to work on those individually, and then once we start getting people finished their individual problems, I'll start putting them up. Okay, yep. Another hard copy, I believe I do. Got to figure out where it is. 3, 4. Okay, I may have 4, we will see. That's the old one. That's another old one. And I think that's the one I want. Okay. Okay, there we go. So that's a very good example of why I really do like students asking questions, because it's almost always the case that if one student has a question, you've got 5 or 6 other people with the same question, right? So try not to get too shy about asking questions. Okay, so here is a question, and we've got some capacitors, an inductor, a couple of resistors, and a voltage source. Now, the problem with this question is that we're actually not given a value for the voltage source, right? So it's asking you to mostly or partially do this algebraically, right? To find a relationship between I out, the thing we're trying to find, which is this thing here, and the voltage V angle theta. We are given the operating frequency as 2000 Hertz. So the first thing I usually do with all of these is to make sure I have everything in impedances. So R1 is 100 ohms, R2 is 200 ohms, right? Then L1 is J omega L. Now omega is going to be 2 pi times 2000 or 4000 pi, because our frequency is 2000 Hertz, but omega needs to be in radians per second. So we get J 2 pi times 2000 times L, which is 100 millihenries. So it looks like that. And I haven't started up MATLAB yet. Let me start up MATLAB. And I'm just going to write that as Z01 and then ZC2 and ZC1. ZC2 is 1 on J omega C2, which is 1 on J 2 pi times 2000 times 220 by 10 to the minus 6, and ZC1 is 1 on J omega C1, which is 1 on J 2 pi times 2000, and C1 is 100 by 10 to the minus 6, or 10 to the minus 4. Sorry, say that again? This number here? Yeah, sorry, so the number is going to be 100 millihenries, and I just wrote that out as 0.1 henries, right? 100 by 10 to the minus 3 is 0.1. Okay? So let's just do another script. So ZL1, let's do omega, right? Omega equals 2 times pi times 2000. ZL1 is J times omega times L1. ZC1 is 1 on J omega. And what was C1? C1 was 100 microfarads. Right, and then ZC2, 1 on J omega times 220 times 10 to the minus 6. Okay, so there's ZC2. So that, I haven't actually thought about how to find I naught. Regardless of how I'm going to find I naught, I need to know what those numbers are, right? So I make that's the first thing I do regardless. So how do we find I naught? Any thoughts? Let me see if I can pick on somebody. Not here. Not here. Erythra, how will we find I naught? Yeah, I've been thinking about which way to do it myself, and I think you're probably right. I think mesh is going to be as easy as anything else. Right, I thought about maybe we could do a figure out the voltage up here and then figure out the current through L1 and C2, which is what we're after, but that's going to be about as hard as just doing mesh analysis directly. Yeah? Okay. So let's have a look. So I don't have any polarities. I do want to probably get my second mesh current in the same direction as I naught. So let's just call that one I1, and let's call that one I naught. Right? Now this is the only trouble with mesh analysis is we're going to end up with a vector with V in it. or a matrix equation with V in it, which we may not be able to solve. So let's have a look. So then our I1 mesh is just going to be I1 ZC1. Right. Oh, go for it. I1 ZC1 plus I1 R1 plus R2 times I1 minus I0 plus V angle theta equals 0. And then my I0 mesh is going to be what's it going to be? Let's go with minus V angle theta. Right, plus R2 times I0 minus I1 plus I0 ZL plus I0 ZC2 equals 0. Then we can probably do a matrix equation. Oops. Where we have I1 and I0. It's probably going to confuse me given I1's at the top, but anyway, let's... And then we have minus V angle theta here and plus V angle theta here. You just take those over the other side. And then our I1 coefficient at the top left here is ZC1 plus R1 plus R2. And our R0 coefficient is just R2. Sorry? Minus R2, you're right, correct. And then here we've got a minus R2 again for the I1 coefficient. And then it's R2 plus ZL plus ZC2. And the only thing we can do extra now is to put in the numbers. Right, so let's see about putting in the numbers. So ZC1 R1 plus R2. So ZC1 plus R1 plus R2. I think that was R1 and R2 are 100 and 200. Right, and I'm just going to put that in like that. And then minus R2, minus R2, and then ZL 1 plus R2, was it? R2 plus ZL plus ZC2. Let's see if that runs. Sorry? I didn't define R2. That's a good question. That's a good point. Let's just... So it's going to give me an error. Very good. So I should have put just 200, or I should have defined R2 correctly like I did. Yeah. Very good. Thank you. And is that the one? Right, so I get 300 minus J795, 200 minus 200 minus 200, and then 200 plus what's that, 1256, J1256. So another thing, so let's go back and write that out here. So we get 300 minus 795.8 minus 200 minus 200, 200 plus 1256 plus J12. So we could leave it like that. I would prefer to have it in this format. Right, and that's why I did the inverse or the pseudo-inverse here. You could also do, let's call that. Don't know why it doesn't like. For some reason it doesn't like changing focus. No, oh well. Anyway, I've done the pseudo-inverse there. There's several different ways you can do the inverse of a matrix in MATLAB. There's INV, there's PINV, and well, there's RF if you want to do it that way. We don't have the V angle theta, so we can't use that. Or there's the backslash way of doing it. Right? Let me see if I can't. There we go. Right, so Q1 mat is like that. That way I've got it. And so one way to do it is that. Right. Another way of doing it is this, as I said, the pseudo-inverse. Should give you exactly the same result. Looks like it does, and I think the other way is that way. No. It's that way. Nope, other way around. That way. No. Nope. It's not going to let me do it that way. Oh well. So, the difference between the inverse and the pseudo-inverse. Anybody come across eigenvectors? Yeah? So the inverse here is computed using eigenvectors. You find the eigenvectors and the eigenvalues, and you just invert the eigenvectors, and that the eigenvalues, and remultiply it back together again, and that gives you the matrix inverse. The pseudo-inverse uses a thing called singular values. Has anybody heard of singular values? Singular values are really basically the same or very similar to eigenvalues. The difference is eigenvalues can be complex, whereas singular values have to be real valued. So they're like the square of the eigenvalues. And the reason why I tend to prefer pseudo-inverse versus inverse is pseudo-inverse is generally better behaved numerically. So sometimes you don't get an answer with inverse, whereas you do get an answer with pseudo-inverse. Okay, so let's just put those numbers in there anyway. Right, so it's going to be very small numbers. I don't know whether... Right, so it's going to be 3.353. Let's copy those over. 3.353 by 10 to the minus 3 plus j minus j 343 by 10 to the minus 6. Uh, 29.5 by 10 to the minus 6. Minus 529. J 529. And same thing for down there, so 29.5 by 10 to the minus 6 minus j 529 by 10 to the minus 6, and then 42.1 minus j 793. And that's all by 10 to the minus 6. Right, so that is a way of doing it. I think either of these is fine. This one or the one with the currents on it. The main aim is just to see that you can find a solution. And this question, I didn't say use mesh analysis. I didn't say use nodal analysis. I didn't say use superposition, right? So you're going to have to use both your preferences, but what you know about the different methods to figure out what a good way of solving the question is. Okay, so here's another one, and again I haven't given you any values. Right, there is a capacitor, an inductor, and an op-amp, an ideal op-amp. Even though we don't have numerical values for C1 and L1, we can at least write down what ZC1 and ZL1 is. So ZC1 is 1 on J omega C1, and ZL1 is J omega L1. Now the question is, how do we figure out what's happening? Does everybody remember what properties of an ideal op-amp we can use? Let me see if I can pick on someone. Nicholas, do you know? No idea? Oh, that's no good. William, how about you? Right. There's no... Yeah, exactly. Right. So that's one thing. So one thing we know about an ideal op-amp, right, is no input current. So if we're going to figure out, if we're going to look at the way the current flows, then effectively what we've got is that circuit there, right? We don't have to take into account any current flowing in to the negative terminal, right? Okay, that's one. Let me see if I can pick on someone else. Beata, what's another property of an ideal op-amp? Don't know. Okay, see if we can get somebody else. Justin here? There's Justin. Yeah, okay. Brianna, how about you? No? Okay, I'll take that as 3 or 4 strikes and we're out, right? So the other property is that an ideal op-amp has infinite gain, right? So the output voltage is basically an infinite number times the voltage at the positive side minus the voltage at the negative side, right? So it's not true for a real device, but even for a real device, the number instead of infinity there is 10,000, 50,000, 100,000, right? It's still huge. Okay, so they're the two things. Now there's a follow-up for that infinite gain, right? The follow-up property is because of that infinite gain, the voltage at the positive input is the same as the voltage at the negative input. And because the positive input is connected to Earth, that VE label there is a thing called the virtual Earth. Right? So really, if we put those two properties together, that's the circuit that we've got to analyze, this one here. And the usual way to analyze this is just with nodal analysis. Right, so IL1 equals IC1. Right, the current, well, they're both flowing in, so we can add them and say that they equal 0, so there should have been a negative there, right? So, and IL1, see if I can pick on someone else. Is Kevin here? No. Jocelyn? No? Don't know what the current is. Okay, so let's try someone else. Abigail, any idea what the current is? Well, it's not 0. The current in here is 0. Right? There's no current flowing into there. But if I've got an inductor, and I should really relabel this. The voltage here is V in, right? And the voltage here is V out. So really what I've got is, on the input side, I've just got V in going to the inductor, right? So, and this is ZL1. So the current is just V in on ZL. Okay. On the other side, the circuit is just got the capacitor in it, right? V out. So IC1 is just V out on ZC. It should be a C rather than an L. So then I can say that VI on ZL plus V out on ZC equals 0. And then I can rearrange that and say that V out on ZC equals minus V in on ZL. So V out is just minus ZC on ZL times V in. Right, and that's all that one's doing. This is just this is a bit different from the circuit we saw in class earlier. The circuit we saw in class earlier just had a resistor in the feed forward path and a resistor in the feedback path. But the outcome is exactly the same. It's just instead of having RF on R1 or RB, it's Z on Z, right? And it's an inverting amplifier. Even more, it's actually a frequency dependent inverting amplifier. Whereas if we just had R1 and R2 instead of L1 and C1, we'd get a constant gain across all frequencies. But because ZC and ZL change their values, right, let's just plug in the values, right? So ZC is 1 on J omega C, C1, and ZL is J omega L, and that is going to be, what's it going to be? Minus 1 on omega squared LC. Right, because it's like 1 on J omega C times 1 on J omega L. Yeah? Sorry, say that again? So I've got ZC on ZL. I don't have the negative, right? I've dropped the negative, right? But yeah, this is just ZC. So this one is ZC, and this one is ZL. Right, so now I can take this over back here and I can say that that's just, with the minus sign, it's 1 on omega squared LC V in. Okay? Okay. So I think we might be better off just doing some you doing problems rather than me doing problems now. So let's have a look at the phasor problems, and let's see. Let's get the first row here to do option 1, and the second row to do option 2. And the back row to do option 3. Okay, so try doing those, and once I get some answers, I'll put them up. Okay, anybody from the front row got an answer? No, not yet. Okay. Hey, it's me. Testing. Yeah, that's okay. Yeah, it's not too bad. Okay. Smile, you're on candid camera. Sorry. Okay, we got an answer for question 1? No? Anybody got one for question 2? Question 3? No? Okay, got an answer for anything? Yeah? Jocelyn, you look like you got an answer. No? Yeah? Anna, what do you want? $17.28 plus J 23.04, and it'll be amps by the looks of things. Anybody in the back row believe her? Agree with her? Okay, let's see if we can do number 3 then. Right, so this one to me just looks like a current divider, and the trick is we've got to get our ZL, right? So ZL is J omega L. Omega in this case is 25, and 600 millihenries, so it's 0.6. So I'm not going to try and do that in my head. Let's go back to MATLAB. Right, so 0.6 times 25, 15. So J15 ohms. Now we've got 20 ohms on the other side. So our I out should be our I in, or IS, times the impedance in the other branch, J15, divided by the sum of the impedances. Right? And that's just going to be 48 J15 on J15 plus 20. So let's put that into MATLAB. Let's make a new one. This is Tute 5Q. Eek, didn't want that. Right, so our I out equals 48 times, times J15 divided by J15 plus 20. I think that was right. Okay, so let's see what that gives us. And yeah, looks good. 17.28 and J 23.04. Okay, anybody for the second row got an answer for what the voltage across the capacitor is? So the current through the capacitor, so we just want V equals IZ. The trouble is we've only given the capacitance, so we need to figure out what ZC is first. Right, so ZC is 1 on J omega C, which is 1 on J. Omega is 10 to the 6th, or actually 10 by 10 to the 6th, I think. And then times 2 by 10 to the minus 6. So it's 1 on J20. So then our current, our voltage, V equals IZ. So it's 4 angle 25 times 1 on J20. Probably got the wrong numbers. Oh well. This is option 2. Should have done it the other way around. What do they say? 4 angle 25. V equals IZ. 4 angle 25. Right? Times 1 on J20. So that's 0.0845 minus J.181. Does that make sense? .0845 plus minus J 0.181 volts. Right, so we're not finished yet, right? Right, so you go back and I should go back and read the question, right? What is the time domain function? Okay, so we've got the complex, we've got from that we can get the amplitude and the angle, right? So the absolute value and the angle, and I'm going to convert that into degrees and see what that gives us. Right, so it's 0.2 and minus 65. So to write it out as a, oops, we want that one. Right, so to write it out as a function of time, it's going to be 0.2 cosine. Now we're not going to change the frequency, so it's still 10e6t, and then the angle is minus 65 degrees. Right? Now you possibly should have guessed what that angle should be. Why I say that is because we just have a capacitor. And we're putting in a current with an angle of 25 degrees. And we just have a capacitor, and we know that the impedance of the capacitor is minus J something. Right? Minus J something is a negative 90 degree on top of the 25 degrees. So you should be able to say, well, it's 25 degrees minus 90 degrees, and funnily enough, that gets us the minus 65 degrees. It's harder when there are resistors in there, because then you don't just have plus or minus 90 degrees, right? If it's an inductor, you get plus 90 degrees. as a phase, where a capacitor you get a minus 90 degrees as the phase. In MATLAB, yeah, so I use ABS and angle. The other thing you could do is you could use ATAN2 and get the imaginary part of V and the real part of V. That'll also be in radians, so if you want it in degrees, right? That's another way. Angle is just a shorthand for that ATAN2 way of doing things. And it's ATAN2 because if you don't pass in both the imaginary and the real part as separate things, ATAN just gives you in the left half, an angle in the left half plane. It doesn't give you, you can't disambiguate between negative real and negative imaginary and positive real and positive imaginary. In this case, it'd be ATAN would be fine. Because it's in the image. Wish I could type, it'd be wonderful. And let's get it in degrees again. Okay, that's in an appropriate quadrant, so the standard ATAN function gives you the right number. Okay, let's have a 10-minute break, and when we come back we'll do a couple more problems. I'll get everybody to do a couple more problems, and then we'll talk about labs today. Okay, but let's have a 10-minute break for now. Why am I searching on Yahoo? That's no good. Who would ever? Settings, search engine. I wondered why they That's what I was after. Okay, gonna grab a coffee. Okay, I don't think I actually answered question 1, did I? That was remiss of me. Do we get an answer for question 1? No? That's no good. Oh, really? Okay, so one way to think about question 1 is vectorially. And that means we can effectively ignore the 50t for now. So 10 angle minus 60, so minus 60 is down this way, right? And maybe that's 10 long there. And then 12 plus 30 is up here, right? And it's 12 long. And the way you add things vectorially is you take, say this is, well, V1 is the blue one. What you do is you take V1 and you start V2 from there, and then the answer starts at the origin where V1 started and goes to the tip of V2. Right, that's one way to think about it vectorially. But I just did it in MATLAB. Figure out where that is. I think it's that one. Right, and we can run that. So I put V1 as 10 e to the I theta, and V2 is 12 e to the I theta, where theta in the first instance is minus 60 degrees, but I've converted it to radians, and theta in the second instance is 30 degrees. And again, I've converted it to radians because exponential doesn't like degrees. Okay, so then the rectangular coordinate answer is 15.39 minus j 2.66. 15.39. Right, volts, but we probably want to convert it back into a V of t. So we need to go back here and say make that equal to V total, and then do what we did, find the absolute value of V total and the angle of V total, and give it in degrees maybe. Right, so it's 15.62, angle minus 9.8 degrees. So that's 15.62 cosine 50t minus 9.8 degrees. Option 1 didn't actually explicitly ask for the time domain version, but I thought I might as well do the time domain version as well. often good to do both the rectangular answer and the polar answer, and then the time domain version is just a small step, right? So the polar version would be 15.62 angle minus 9.8 degrees, and then the you should still be able to. Most of these should be reasonably easy to do on the calculator. Okay, well, can I borrow your calculator and let's try and so let's have a look. Let me come over here. Which orientation it has. That way, maybe? There we go. Just going to grab my computer so I can pull the question out. Right, so the first question is 10 angle minus 60 plus 12 angle plus 30. Right, so I would do that as 10 times. Now I've got to get used to exponential I, and was it minus 60? So minus 60 divided by 180 times pi. Right, so there's that one. And then plus, and it's 12 angle 30. So 12 times exponential I, and this one's 30 divided by 180 times pi. And I think that's the same as what we got before, right, in MATLAB. Now, what I would like to do is take the magnitude of that. Well, there's the angle, I think. No, that's not what I want to do. Second mode, okay, yeah. Okay. Now, what I'm not sure about is, as I said, is how to get the absolute value of that. Okay, so there's the absolute value. Now, can I get answer in there? There we go. Right, so that's how you get the answer, and then the other one was right, math, and you'll want angle. Now, answer won't work, so. Right, and there's the minus 9.8 we got before. Okay? So that, I mean, it should be doable. You're welcome. Oops. And I should turn that back on, shouldn't I? Maybe? There we go. Okay. So I'm just going to do this one quickly so that we can be complete, right? So this one, we've got frequency of 1500 Hertz. Remember, we've got to multiply by 2 pi to get omega. So omega is 3000 pi radians per second. And so our ZC is 1 on J omega C, which is 1 on J 3000 pi times 10 by 10 to the minus 6. And our ZL is J omega L is J 3000 pi times 0.023. Right, or 2.3 by 10 to the minus 3 if you want to do it that way. It's just the same way as combining resistors, but now we're talking impedances, right? So the yellow one is going to be, let's call that ZR2C, and that's going to be 2000, which is R plus ZC. I'm not going to type in ZC just yet. And then that ZR2C, the combination of the 2K and the 10 microfarads, is in parallel with ZL. Right, so let's do that. Let's call it ZLR2C is equal to 1 on ZL plus 1 on ZR2C. And then the overall thing is just in, that whole thing is just in series with the 1K. Right, so ZTH is 1000 plus ZLR2C. And now I'll go back and plug some numbers into MATLAB to get that to work. So we do a new one, save that, and got the numbers wrong on that. So omega is 3000 pi. Let's start with that. And then ZC is 1 on J omega C. And ZL is 2.3, is J omega 2.3 by 10 to the minus 3. And then the first one, ZR2C, is R2 plus ZC. And then ZLR2C is 1 on ZL plus 1 on ZR2C. And then ZTH is 1000 plus ZLR2C. Right, so it's going to be 1000 plus J21, 21.68. If you want to go to full significant figures. So 1000 plus J 21.68. And again, units of ohms. Is that okay? Yeah. Okay, so this next series of questions is about superposition, but this time we've got impedances rather than just resistors. But it works exactly the same way, right? You you keep one of the independent sources and you replace all the other independent sources with their ideals. The voltage source ideal is still a wire. You just turn the voltage down to 0 and it's as if there's no source there, so it's just a short circuit. And the current sources, you turn the current down to 0. And turning the current down to 0 means nothing happens. Where there's no current flowing, so it's an open circuit. Right? And I think I'll get, so option 1, if the front row can do that, option 2, the middle row, and option 3, the back row. And I'm going to have a play while you do that with option 4. 7095. Hmm. 9.9. 9.9. It's pretty much just 9.9. Okay. J4 angle minus 120. So that's 40. Now I3 we've got 65, 95, 95 plus J4, I3, that equals J16 angle minus 120, J, so it's 16 angle minus 30, I think. Minus 120. Yeah, minus 30. Looks like it's the same as A1, and B is different. -40 -120. -16. $19.09. You've got it the wrong way around. That's wrong. So let's try that again. That one should be the same, but that one's going to be different. $9.903, angle 0.5. .1. That's what I got before. That's right. Okay. -0.6 minus J19. .08. Oops, without the minus. Which is 19 angle minus 92. It's 9.25 minus J 18.98. Minus J. Any answers yet for any of them? I think I've managed to do the fourth one. I'm just going to go grab another swig of coffee.
have a system of linear equations with complex numbers. J is the square root of -1, which is sometimes called as I. X and Y are two unknowns. And like the real case, you can just take the coefficient matrix here and change this into AX equal to B type matrix equation. Now, if you want to solve this using the RREF method, you should put these two matrices into a single matrix like this, and then all you have to do is just plug this into your calculator and do the RREF if you have TI-89. Now, the trouble with TI-83 is that you cannot put, it doesn't allow you to put complex numbers into matrices. So you have to do this very complicated way of solving the equation using real matrices. And at the end of the video, I hope you can manage it, or you might just decide to buy a TI-89. Okay, but let's see how it goes. Now, the key to changing a complex matrix into a corresponding real matrix, so you can just plug this into the calculator to solve, is to change a single complex number into a 2 by 2 matrix. How do you do that? Well, first think about this 3 plus j as 3 plus 1j, and put those two numbers 3 and 1 as a column vector. So you have 3 and 1 up and down. And then you have to put another column right next to it, and the way you do it is you flip these two numbers. 3 and 1 gets flipped into 1, 3, and then you have to negate the top one. Okay, so you have to, and you have to do this for every one of these elements, even if the number is real.
Okay, so if in this case you've got a 2 by 3 matrix, and he'll go on to do it, but it's going to end up with a 4 by 6 matrix. It's just double the size. Okay, let's just quickly see.
So what it does is it makes, even if it's real, we still need to change it to 2 by 2. To do that, you think of -2 as -2 plus 0j, and therefore you put -2 and 0, and then again you flip and negate the top. Here we also have 6, and also it's much faster to plug it into the calculator.
He started off with the complex matrix at the top, and where he ended up is with the purely real matrix. Okay, so each 2 by 2 block in the big matrix is just one element of the complex matrix. Okay, now it looks it's a bit tedious, but it's not that difficult. The trick is then when you do RREF, you again end up with the unit matrix on the left-hand part of the result, but then you get two non-zero columns on the right-hand side, and they're going to have the same symmetry, right? So it's going to have each 2 by 2 block on the right-hand side is going to be a complex, represent a single complex number. And actually I think the one you've got to read is actually in the output. It would be the second, the second column there, because the other one, the top one, will be the negative of the imaginary component, then the real, then the negative of the imaginary, then the real, whereas the second one in is the one you should read. Let's just see if he's got see if he actually does the RREF. So there's the result. As you can see, you get the identity matrix, 4x4 identity matrix with ones on the diagonal on the left. And then the actual answers is not the far column, but the one in from the far column. So you get 2 minus j and 2 plus 1.5j. Okay? Okay. Anybody got any answers? So I did I did option 4, right? And the first thing I did is I identified the frequency is 2000 radians per second, and then I calculated ZC and ZL, minus J2 for ZC and J4, both ohms, for ZL. And then I decided to do the voltage source first. So I set the current source to its ideal, which is an open circuit, and that worked out. So that bottom left wire no longer exists in the circuit. And I did that analysis. I just used mesh analysis to answer that. And in the end, I got that the first output voltage, the component of the output voltage that's generated by the voltage source, is just 40 times that I2, which is 9.9 plus J.1 volts. And then I did the same thing, but this time I replaced the voltage source with its ideal, which is a wire. And then I did mesh analysis again. I chose my I1 to go in the same direction as the current source, so I1 is just given directly. Right. Then I did the I2 mesh and the I3 mesh. And I ended up with basically the same A matrix in both cases. Right. Those two matrices are the same. The only difference is now I've got some different things happening here. And that gave me the voltage output generated by the current source. And then superposition says that adding those two together, there's my V out 1, V out 2, gives me my total. And I can just add those two together to get the final output. I'm not going to go through that in a huge amount of detail. I probably made some mistakes because I didn't have you watching me while I did it, so expect there to be mistakes. Okay, has anybody got an answer for any of the ones you were doing? Jason, you got an answer. So you're option 2, yeah? Two plus J.9, 9.3. sorry, 2.34 plus J 9.384, and what are we after? We are after the output voltage. Okay, could you tell me the individual components? Well, so it's doing it with superposition, so you... Oh, you just did you just did mesh analysis. Okay. Okay, so the aim was to do it using mesh analysis, but that's okay. Okay, so that's yeah. Right, so the aim was to do the analysis with the yellow ones first. Oh, you did? Okay, oh, it was just after the individual numbers, that's all. Oh, and then, yeah. Well, that's okay. Just tell me the currents individual, that's okay. 1.7719, yeah. Sorry, J 054, okay. And then you just multiplied the impedance of the, yeah, okay, that makes sense, that's good. Yeah, I mean, that's actually a really good thing to remember, right? When you're doing superposition, everything adds up, right? Not just the V out, but the currents add up, the voltages across each of the individual components add up. Okay, anybody got an answer for option 1 or option 3? No? You got one for option 3? Okay, go ahead, Abigail. Sorry, 4.05 plus J 0.45. And that was for I out. Yeah, so that's in amps. Could you give us the individual numbers too? Yeah? 4.2, sorry. 4.225, yeah? 4.15? Sorry, plus 15, 617. And again, that's amps. So one thing I'd like to do is to, even if I don't know the exact answer, I like to check to see if the magnitudes look about right? And just seeing here, right, we've got 8 amps coming out of there, and we've got a 40 volts here. The impedances are in the tens, so 40 volts with in the tens means we've got about a 4 amp. So 4 and 8 is about 12. So that's looking about right, right? I'd worry if the numbers were like the answer was 40 and 110 versus what I was getting before, or the other way, right? If they were 0.4 and 1.1, then I'd worry that there was a magnitude problem. But that looks like it's in the right ballpark. Anybody got one for question 1? So you're keeping the voltage source and you, yeah, okay. Sorry, minus 0. Sorry, 1.0129, yeah. Okay, so lots of zeros, 41. Yeah, and that's going to be one more 0, okay. Okay. And that was which? That was keeping the voltage source, or keep? Okay. So how would I do the other one? I'd really just be tempted to do a current divider, right? Because the other one looks something like there's our current source, we're keeping that. There's the thing we're after, our I out. And then everything else that's 20. And that one's 40. Right? So I'd be tempted to do that, put those together, right, as a single equivalent impedance. And then you've just got a current divider. Now my main problem is just it's going to be negative, so I out is going to be minus impedance in the other branch, which is ZEQ, divided by ZEQ plus ZC times whatever it is, II. And that'll be IO2. We've already got IO1 up there. So that's the way I'd do that one. Okay. I want to leave this tutorial here now. I'm going to continue it next week. I do want to talk about the 2 labs, right? So we've got to finish off the Thevenin lab, and you're going to need to partner up, and I've gone off and soldered some wires so you can actually connect up your circuits to a potentiometer. Let's just quickly have a look at what's happening there. Where it got to? Did I not put it in lab 6? Lab 7, there it is. So remember what that potentiometer is doing, right? It's got 3 connectors, and if you measure the resistance between, I don't know whether I've got any cords. Let's try it. It's probably the wrong ones. Crunch. Alright, so I'm just going to use this one. Right, so what I've got here is I'm measuring the resistance between 1 and 3 without this being connected. And I hope you can see it's reading 8.9 kilo ohms. Remember, the resistors we've been using are about a 5% accuracy. So the nominal value, the real value is within about 5% of the nominal. Potentiometers tend to be even less accurate. Right, that's why it's reading 9 kilo ohms instead of 10. And there's a 1K one. Let's see what it reads. It's a bit closer, 0.966. Right, let's see what happens. I'll go back to the 10K. But this time I'm going to connect it up like it is in the diagram. Right, and now I've got 3.7. You won't be able to see it maybe, but maybe I can fix that. Let's see if I can do that. And pull that up. Bring this over here. Right, so there's the potentiometer, and I'm just going to twist it, and it goes down to 1.6 ohms. And then I twist it all the way up the top, and I get my 8.9 kilo ohms. Right, so that's what happens when I connect it up like the diagram. Okay, so and what we're going to be doing, now remember I made the mistake, some of these are 1K, so if you've got a 10K, then get a 1K ohm resistor for R1. But if you've got a 1K ohm potentiometer, get a 100 ohm. Okay, and we're just going to connect it up like this. The only difference is I want you to instrument it. So you measure the current and the voltage across the load resistor. Now in order to do that, you need 2 meters. So you're going to have to work with somebody else in order to have the 2 meters. Now I'm hoping you can move the 2 meters close enough to each other so that they work. I think somebody's gone in and chained everything down, so it might be a bit hard to move things around. Right. So that's the first thing. That should be relatively straightforward. The only painful thing is you're going to have to do several measurements, right? So there's 10, probably about 20 measurements. So you're going to move that potentiometer, start it with it all the way one way and then just gradually turn it and get about 20 measurements. Now you're not going to be able to measure RL, right? You will be able to measure the voltage across the load and the current across the load, current through the load. So what I want you to do when you report is to put what you calculate RL to be at each position. You'll be able to do it by, you've got the measurement for the voltage, you've got the measurement for the current, V equals IR, so you can calculate what the resistance was. If you don't do that, what you've got to do is take the potentiometer out of circuit, measure the resistance, put it back in the circuit, measure the voltage and the current, and that's going to be a whole other level of pain, right? So I suggest you just connect up 2 meters, one for the voltage, one for the current, and then calculate what the resistance was and do about 20 measurements. Okay? That's the first one. And then the other one I want to try and do today, and it doesn't matter if we can't because we can do it next week, is I want you to have a look at the oscilloscope. Right? And we haven't touched an oscilloscope before. So let me go back there and have a look at the oscilloscope. So there's 2 devices that we haven't used yet. One of them is the oscilloscope, and the other one is the other big screen looking thing. That's the signal generator. Right? I might just go grab one of these, I think. There we go. Right, so let's talk about the oscilloscope. This is the oscilloscope. It's got a total of 4 inputs, right? Those inputs there maybe, right? These inputs, you use one of these, right? They're different. The other sort of BNC connector we've got is for the is for the signal generator. It's a lot thinner and it's silver, whereas the ones you want to use on the oscilloscope are thicker and black. Now what oscilloscopes do is they let you see the voltages, right? We're going to be using sinusoidal voltages, and the labs the first lab, the phase one, we want to see the phase, right? We want to put in a sinusoidal voltage, and we want to see that the voltage phase is different from the current phase when we've got the voltage across a capacitor or an inductor. Now there's lots and lots and lots of buttons on these things, right? The ones that are really useful, well, firstly, there's the on button. It's down here. Can you see that? Maybe not. Yeah, there you can. Right, it's that one there. That turns it on. Inputs are those 4 BNC connectors there, bayonet connectors. We will only need to use 2 of them, so don't worry too much about it, about the other 2. They're color-coded, so the thing you can see on the screen now, channel 1 is yellow and channel 2 is blue. Channel 3 is pink and channel 4 is green. I've only got channel 1 and 2 turned on. Let's see if I can turn on channel 3. There's channel 3, there's no input. And there's channel 4, there's also no input. Right? Oscilloscopes are instruments, so it's nice to be able to know that they're actually calibrated appropriately. And what I've got on the screen is the calibration signal. And over this side, whether I can move that around, maybe. Right, over this side, there's 2 bars. The top bar here, can't quite see that properly. Too much reflection. There we go. The top bar here is earth or ground, and the bottom bar is the calibration signal. The usual calibration signal for oscilloscopes is a square wave, right? Turning on and off, and usually between 0 and 5 volts. I think that's what this one is. Doesn't actually say, but let's have a look. You'll notice that the yellow square wave is bigger than the blue square wave. That's because the channel 2, the blue one, is on a different range. Right, I should be able to get them wave inspector. There we go. Right, so I've now changed the scale on the blue one, so it's on the same, and it's the scale is called volts per division. It's a bit hard to see, but there are actually graph lines on the screen. Just dotted lines, and each of those vertically each of those is currently 1 volt per division. Right, that's what this is saying here for the blue channel. And I think there's 1, 2, 3, 4, 5 divisions. So the peak to peak voltage is 5 volts. I can also change the horizontal scale, right? Depending on what frequencies I'm looking at. So here I'm looking at lots and lots and lots of periods of the square wave. Now, one thing that gets really confusing for people who are new to using oscilloscopes is sometimes I don't get a nice static display. I get something like this, right? And it's really hard to measure stuff when it's doing that, right? So what you've got to do, what I just changed, you can see there's a tiny little yellow arrow in the top right of the screen, right? That tiny little yellow arrow is telling me what the trigger voltage is. And the trigger voltage is the voltage at which that graph starts across the screen. At the moment you can see the trigger voltage is above the 5 volts, above the top value, and that's why it's not triggering. It's not starting at the same point in the cycle every time. So what I have to do I have it there? This panel here is called the trigger. The only one you probably need to play with is the knob, and I need to bring the trigger level down so that it's triggering on the right place. And now it's nice and static, and that's happening because the trace is starting at the same voltage every time. Because it's starting at the same voltage every time, and because the waveform is a nice regular waveform, it looks like it's stationary. It's not. It's going across lots and lots and lots of times a second. But because it's going so quickly, we can't see it. Okay. Just trying to think if there's anything else I need to tell you. Most of the measurements are written down on the bottom. We may need to I might have to spend some time with this oscilloscope myself. So what you can do is you can add, they're called cursors, to the screen. So you can say, okay, I want to measure vertically between this level and this level. That'll give you a voltage difference. Or you can measure this way, and you want to measure between this time and this time, and that'll give you a time difference. you'll notice that here we've got a few things. We've got a delay. That delay is going to be a time measurement. There's also phase, right? Phase is something we're more interested in. That's the theta we've been dealing with in all of our circuits. Now, I'm just not quite sure. There we go. No, I'm going to have to play with this a bit more because it's a little different from the last scope I used. It's got the same functionality. I just don't know which buttons to press to get it to work. Okay, so that's that one. Let's quickly have a look at the signal generator. Right, there's the signal generator, there's the power button. Think about the signal generator just like a power supply. And just like the DC power supplies, it's got two power buttons. It's got the on button, which I just pressed, and it takes a while to boot up by the looks. And it's also got an output on button, which is this one here. Right? Now, I want to get, and again, I haven't, okay, so in order to set the frequency, you double tap the number there, and then you can say if you want 100 hertz, 100 times 1, and it'll give you 100 hertz. Right? So there's my sine wave. It's selected here. You can see it's lit up as sine wave. It's continuous. So now what I should be able to do is turn that on. And let's see if I can show it. I might have to do it on channel 1. Get the right triggering happening. Let me just we go. Go triggering. Let's move it up a bit. Right, so what I've done is I've connected the signal generator to the oscilloscope, to channel 1, this one. And you can see that I have a nice sine wave. And I set it up initially to have a frequency of 100 Hertz. But I can change that to 200 Hertz, right? So it gets faster, or I can change it to 10 Hertz maybe, and it gets much slower. We're going to use that signal generator to generate a sine wave to excite a circuit with a resistor and a capacitor, or a resistor and an inductor. Right? And you're going to have to set the frequency. Okay. Any questions about either of those two devices? Has anybody used either of them before? Once? Okay. That's all right. So what I suggest is let's get into groups of 2, so that you've got 2 meters, and grab one of the potentiometers and do the measurements for the maximum power transfer part of the Thevenin. And we won't have time to do the next lab, the one with the oscilloscope, but try just turning on the oscilloscope and try seeing those what do you call it, calibration signals, the square waves. Okay, what do I need here? I think that's all I need. Grab those 2. Get out of your way. And just make sure you know which number you got, right? 10K or 1K. Okay, I'm going to turn down the yeah, thank you. Grab that one.